Imagine you are trying to measure exactly 1 cup of water scooped out of a bathtub. Now, add a complication. The water in this tub isn't calm. It is violently sloshing back and forth, creating tall, chaotic waves. To make things even harder, the drain is slightly open. So while those waves are crashing, the overall water level is continuously dropping. Right in the middle of all this chaos, a robotic arm swoops down, scoops out a tiny cup of water, and disappears. How do you calculate the exact volume of water that arm just removed, using only the water that's left? The easiest approach would be to measure the average water level before the scoop and compare it to the average level after. But in a messy environment like this, simple averaging fails. Because the overall water level is constantly draining and the waves are so high, an average reading accidentally counts the leaked water and the wave heights as part of the scoop. This exact measurement problem happens thousands of times a minute inside modern vehicle engines. The engine has its own version of the bathtub. It's called a fuel rail, a heavily pressurized pipe that holds liquid fuel ready to be used. And instead of a robotic arm, the engine uses a fuel injector. It fires a tiny electrical pulse to squirt a precise amount of fuel out of the rail and into the engine. For years, the standard for measuring this squirt was called pressure drop analysis. The computer simply averaged the rail's pressure before the squirt and compared it to the average pressure after. That older method works fine for low-pressure gasoline engines. A low-pressure fuel rail behaves like a calm, perfectly still bathtub. But this chart shows why that fails in high-pressure systems. High pressure causes massive pressure waves. That's the sloshing. These systems also have tiny, constant leaks, like that dripping drain in our bathtub. High-pressure engines require a new way of thinking to cut through the intense physical noise and find the true injection amount. To solve the sloshing and leaking, the engine control unit uses a much smarter mathematical approach. This graph illustrates the solution. First, the sensor gathers a cluster of the messy, sloshing pressure data right before the injection occurs. Next, the sensor gathers another cluster of messy pressure data after the injection event has finished. Instead of taking a flawed average, the computer looks at the trend. It draws a line of best fit right through the downward sloping waves before the squirt, and another line through the waves after. Then it continues those lines inward, following their path toward the exact center of the moment the injector was open. The vertical distance between those 2 points is the true isolated pressure drop. By drawing those trend lines, the computer accounts for the continuous leak and cuts right through the middle of the sloshing waves. The noise is erased, leaving only the exact measurement of the scoop. Looking back at our bathtub, this math effectively freezes the sloshing waves and plugs the leak, giving us a perfect reading of calm water before and after the robotic arm dips in. Inside the vehicle, the electronic controller box takes that perfectly isolated pressure drop reading from the fuel rail. It instantly references a digital rulebook, a lookup table. This translates that specific drop in pressure into the exact physical weight of the fuel injected, down to a single milligram. Modern engines require absolute precision. If the computer thinks it injected 2 milligrams but actually injected 3, the entire combustion cycle is thrown off. By knowing the exact amount of fuel entering the combustion chamber, the engine can adjust on the fly. That precision ensures a smooth, powerful ride, maximizes fuel economy, and keeps the air clean. It takes a simple idea, drawing a clear line through physical noise, to solve one of engineering's most chaotic measurement problems.